Hello guys, so today we are going to prepare an experiment for determination of caffeine in tea using second derivative ultraviolet spectrophotometry or UV-VIS with background correction. So let's get started.
Preparation of standard solutions. We prepare caffeine standards with concentration of 0, 10, 20, 30, 40, and 50 mg per liter. Then, 5 ml of each standard solution was transferred into dry test tubes. After that, 0.25 gram of 0.025 molar copper acetate and 1 ml of 1 molar sodium hydroxide were added into each tube. The mixture was shaken vigorously to ensure complete mixing. Next, the sample were centrifuged for 10 minutes to separate the precipitate. The supernatant was carefully collected without disturbing the precipitate. Lastly, the first and second derivative UV spectra were recorded.
Caffeine extraction from tea. First, the tea bag was weighed and the mass was recorded. The tea bag was then placed into a beaker containing 200 ml of distilled water and boiled for 50 minutes to extract the caffeine. After boiling, the solution was allowed to cool slightly before filtration. The filtrate was transferred into a 250 ml volumetric flask and diluted to the calibration mark with distilled water to obtain the stock tea extract.
Dilution of sample. 5 ml of the stock tea extract was pipetted into a 50 ml volumetric flask. Distilled water was then added up to the mark to prepare the diluted tea sample.
Next is sample preparation for a UV triplicate. 5 ml of the diluted tea sample was transferred into 3 separate dry test tubes for triplicate analysis. Then, 0.25 gram of copper acetate and 1 ml of 1 molar sodium hydroxide were added into each tube. The mixtures were shaken thoroughly and centrifuged for 10 minutes. After centrifugation, the supernatant was collected carefully. Finally, the first and second derivative UV spectra for each sample was recorded.
This slide shows the use of an external standard calibration curve in UV-VIS analysis. A UV-VIS spectrophotometer does not measure concentration directly. Instead, it measures the absorbance value at a specific wavelength. To determine the concentration of a sample, several standard solutions with different known concentrations are prepared first. The absorbance of each solution is then measured, and the calibration curve of absorbance versus concentration is plotted. From this graph, a linear relationship can be obtained based on the Beer-Lambert law, where higher concentration gives higher absorbance. Finally, the absorbance of the unknown sample is compared with the calibration curve to determine its concentration.
Procedure for UV-VIS spectrometer. First, switch on the computer and click on UV-WinLab software. Then choose CHM580 MSC method. Next, for the wavelength, make sure it's in range between 350 nanometer to 190 nanometer. Then click sample and change sample name to your likings. Below shows example. After that, prepare sample into the cuvette. Make sure to wipe the surface clean. For the laser form UV-VIS, scan the sample without interference. Press setup immediately to save the setting methods and wait for auto zero and start button on top of the software lights on. Then click auto zero and click OK after making sure you enter the right sample. Next, click start to run sample and blank sample will start to run and showing result as B video above. Lastly, repeat the step for next standard solutions.
The UV-VIS spectra showed a maximum absorption peak, lambda max, at around 270 nanometers for all samples. Higher concentration samples produced higher absorbance values, showing a direct relationship between concentration and absorbance, according to the Beer-Lambert law. The blank sample showed nearly zero absorbance, confirming that the solvent did not interfere with the analysis. Overall, the UV-VIS analysis successfully identified the characteristic absorption peak of the samples. This page shows the external standard calibration curve for caffeine using UV-VIS first derivative analysis at 271.81 nanometers. The absorbance values increased as the caffeine concentration increased from 0 to 50 milligrams per liter. This shows a direct relationship between concentration and absorbance, following the Beer-Lambert law. The highest absorbance recorded was 1.1992 A at 50 milligrams per liter, while the blank solution showed zero absorbance. Overall, the calibration data produced a good linear trend, indicating that the method is suitable for determining caffeine concentration quantitatively.
Next, this slide shows the relationship between the second derivative spectra and the external standard calibration curve for caffeine analysis. From the second derivative spectra, we can observe that the peak intensity at around 293 nanometer increases as the concentration of caffeine standard increases. The higher concentration standards produce larger derivative signal values, which indicates a direct relationship between concentration and absorbance response. These derivative values were then used to construct the external standard calibration curve. In the calibration graph, concentration is plotted against the second derivative absorbance at 293 nanometer. The high R2 value indicates excellent linearity and confirms a strong correlation between the second derivative spectral response and caffeine concentration. This means the method is reliable for quantitative analysis.
The calibration curves plotted can be used to determine the concentration of caffeine in the sample by substituting the absorbance value into the calibration equation obtained from the graph. For the first derivative, the calibration graph equation obtained was y equals to 0.0243x plus 0.0749. In this equation, y represents absorbance and x represents caffeine concentration in milligrams per liter. For sample 1, the absorbance value recorded was 0.73195, and by substituting this value into the equation, the calculated concentration obtained was 27.0391 mg per liter. The same calculation was repeated for samples 2 and 3. Moving to the second derivative, the calibration graph equation was y equals to 0.0153x plus 0.019. For sample 1, the absorbance value was 0.28555, and after substituting into the equation, the concentration calculated was 17.4216. Overall, the first derivative method produced higher concentration values compared to the second derivative method.
The second derivative spectra is considered better because it provides better peak resolution and effective background correction compared to the first derivative spectra. First derivative graph, some peaks are still broad and overlapping, difficult to determine exact wavelength and concentration accurately. While for second derivative spectra, it produces sharper and more defined peaks, allowing small spectral differences to be detected more clearly. The second derivative can perform background correction. Baseline drift, noise, and interference from solvents or other component can affect normal absorbance spectra like the first derivative. By applying the second derivative treatment, the constant background signal is minimized and resulting in a flatter baseline. This improved the accuracy of analysis because the measured signal mainly represent the analyte. The concentration in second derivative spectra is achieved as the derivative peak intensity changes proportionally with increasing concentration. As the concentration increase, the derivative signal becomes stronger and more distinguishable at selected wavelength.
Before operating the UV-VIS spectrophotometer, ensure that the instrument is properly connected to the power supply, the cuvette is clean and correctly placed, and the required wavelength and measurement parameters are properly set for accurate analysis. Here we can see the internal components and working principle of a UV-VIS spectrophotometer, an instrument used to measure the absorbance or transmittance of ultraviolet and visible light by a sample. First, the light source. It contains two light sources, which is a deuterium lamp for ultraviolet light and a tungsten lamp for visible light. These lamps provide continuous radiation over a wide range of wavelengths. The emitted light enters the monochromator, which contains a diffraction grating. Its function is to separate the light into individual wavelengths and select narrow beam of the desired wavelength for analysis, and then the selected wavelength passes through the entrance slit. This slit narrows the light beam and improves the accuracy and resolution of the measurement. Next, sample compartment or cuvette. The monochromatic light then passes through the sample solution placed inside a quartz or glass cuvette. During this process, the sample absorbs part of the light energy depending on its concentration and chemical properties. After passing through the sample, the transmitted light reaches the detector, usually a photodiode detector. The detector converts the transmitted light into an electrical signal. Lastly, The electrical signal is amplified and processed by the electronic system of the instrument. The instrument compares the intensity of incident light and transmitted light to calculate absorbance or transmittance.